This is the screencast for section 6.5, example 5, tracking a moose population. So we're actually going to go through a logistic growth differential equation and solve for P, so find the actual population function. This is going to be long, this is going to be horrible, so grab a snack, some coffee, whatever it is you want to do. Alright. So in 1985 and 1987, the Michigan Department of Natural Resources airlifted 61 moose from Algonquin Park, Ontario, to Marquette County in the Upper Peninsula. It was originally hoped that the population P would reach carrying capacity in about 25 years with the growth rate of this formula. Again, logistic growth because of that limiting factor. According to the model, what is the carrying capacity? So the carrying capacity would be this 1,000 moose. With the calculator, generate a slope field for the differential equation. So what I did was I put in the differential equation 0.0003y, parentheses 1,000 minus y, parentheses, so that P is y, your output. I set a good window and then found my slope field, which does look like logistic growth equations. So far, so good. Now here's the long part. Part C. Solve the differential equation with the initial condition P of 0 equals 61 and show that it conforms to the slope field. Okay, so first we're going to take the differential equation dp dt and multiply both sides by dt, so I get the differential dp. Now I want to separate my variables, so I have to divide both sides by p times 1,000 minus p, so I get all the p's with the dp and anything else with the dt. Now I'm ready to integrate. Wait, no I'm not. How are you going to integrate 1 over p times 1,000 minus p? Because that would be a p squared in the denominator, so a composition function, but the numerator doesn't have a p in it to relate to a derivative. U substitution is out. I don't really see this going well with integration by parts, so guess what? Here's where your partial fractions come into play. So if I have a degree in the numerator of 0, degree in the denominator of 2, I can set up some partial fractions so that this 1 over p times 1,000 minus p can be rewritten as a over p plus b over 1,000 minus p. Which means then that a times 1,000 minus p plus b times p, so finding a common denominator, the numerators would equal the old numerator 1. So I'm going to choose p to equal 0, and that'll help me get that a equals 0.001. I'm going to choose if p is 1,000, then b is going to equal also 0.001. How convenient. So I'm going to plug those in. So I get 0.001 over p dp, and then plus 0.001 over 1,000 minus p dp, and then equals our right side that didn't change. So I can integrate all of those separately. So now I have p in the denominator, which means I have the integral of 0.001 as the coefficient, natural log of the absolute value of p. And then I can continue that pattern. Now this one I would have to subtract 0.001 natural log of absolute value of 1,000 minus p because that is a minus p, so I kind of have to divide by du. And then on the other side I get 0.0003 now with the variable t, because that was a dt, and then of course plus c. Now I don't like all those coefficients out in front with those teeny tiny decimals, so I'm going to multiply everything by 1,000. Also, I don't need the absolute value anymore because the situation that we're dealing with is a population. We don't have negative moose in a population. So now those coefficients become a lot cleaner and I don't have absolute value anymore. Now I changed this second term to a plus the natural log of 1,000 minus p all over -1. So now what I can do is multiply everything by -1, and I'll show you why that's important in a second. Now the natural log of 1,000 minus p, the binomial inside the log, is positive, and I'm subtracting the natural log of p. So I have a log function that can combine those two logs being subtracted with the same base can be combined by using division. And now the denominator would just be p, as opposed to the denominator being 1,000 minus p, which is more complicated. Now I'm going to change this whole thing to exponential form because I am trying to solve for p after all, the population. And now this left side, the denominator can be distributed to each piece of the numerator. So I get 1,000 over p minus then 1 equals, now on the right side here, don't forget, e to an exponent with a sum is really e to the one term times e to the other term in the exponent. So I'm going to make e to the c a coefficient of e to the negative 0.3t. So I'm going to call that a e to the negative 0.3t. Oh, and by the way, when we multiplied c by 1,000 and then multiplied c by negative 1, I didn't have to change anything because c is this constant that we don't know. So eventually we're going to solve for, and now it's an even different constant, a. So we'll just basically solve for this final constant at the end after everything's been done to it. Alright, next, I gotta solve for a. Well, it says the initial population 0, 61. So I'm going to plug in 0 for t and 61 for p. And then I'm going to solve for a, and I get 15.393, which means 1,000 over p equals, now I'm adding 1 to both sides, so that'd be 15.393, the a value, e to the negative 0.3t, and then the plus 1 that I moved over, which now I can take both sides, multiply by p, and then divide by this quotient, basically solve for p, and I get p equals 1,000, the maximum capacity or the limit to growth, all over 1 plus, here's your coefficient, e to the negative 0.3t. I told you that'd be exhausting. But we're not even done. We have to show that it conforms to the slope field. So, in Y2, I graphed the equation we came up with here for the logistic growth, and it does conform to the slope field. So now we're done. But we got an now try problem. The now try problem, number 21, says solve the initial value problem using partial fractions, use a graphing utility to generate a slope field for the differential equation, and verify that the solution conforms to the slope field. So yes, we are in for another one of these large problems. Alright, so dp dt equals 0.0002 p times 1200 minus p. This is a logistic growth equation of population. The rate of change does have a limit. So I can tell you that 1200 is going to go in my numerator at the end of the day today. But let's go start from the beginning. Let's separate the variables. Get all the p's on one side, everything else on the other side. Now we're going to take the antiderivative, but I'm going to use partial fractions here first, which means that a over p plus b over 1200 minus p will equal the old numerator 1. So then if we were finding a common denominator, that means that a times 1200 minus p plus b times p equals 1. So if p equals 0, b gets multiplied by 0, and a would equal 1/1200th. If p was 1200, a would get multiplied by 0, and then b would also equal 1/1200th. Which means I'm taking the antiderivative of 1/1200th over p plus 1/1200th over 1200 minus p dp. That's just messy. So instead, what I'm going to do is multiply both sides by 1200. Oh, and I already took the integral of the right side, 0.0002. The antiderivative is 0.0002t. Now, if I multiply by 1200, that helps me out a lot with those numerators. Those numerators go to 1, and then the right side, that tiny decimal, gets multiplied by 1200, which actually makes it a little bit easier to work with, 0.24t. So I'm going to take the antiderivative of both of these pieces. So I have the natural log of the absolute value of p plus the natural log of the absolute value of 1200 minus p, and then of course divided by -1 because I have to divide by the derivative of 1200 minus p, which would have been -1. And then I have equals 0.24t, and then don't forget that plus c. Now, using the same strategy as before, I want the 1200 minus p to end up in the numerator of my fraction when I combine these logs. So I'm going to multiply both sides by a -1 and then use my log properties to combine. So I get the natural log of 1200 minus p over p, but then equals negative 0.24t and then minus c. And really plus c, it doesn't matter because that's all going to be combined into one big constant at the end anyway. I'm going to change that to exponential form. And of course, like I said before, that would be e to the negative 0.24t, technically minus c, but I separated that to multiplying by the same base. So now I can change a to the negative c, or e to the negative c to a. And I distributed the denominator to get 1200 over p minus 1. So now I can add 1 to both sides and take the reciprocal of both sides and finally get that 1200 is in fact in my numerator. And now I need to solve for a. And I've got that initial value when p equals 20 when t equals 0. So I'm going to plug in 20 for p and 0 for t and simplify. Now I got to multiply both sides by 1 plus a to get a out of the denominator. Distribute, solve for a, and I get that a equals 59. So my final equation then would be the population is going to be 1200 over 1 plus 59 e to the negative 0.24t. So I set my window, of course keeping in mind the limit to growth of 1200, I set my y max to 1500, and then I gave it 50 years. Did a slope field, put the equation we got into y2 and saw that it does in fact fit the slope field.